Hi there YouTube. So sorry for the delay. I know it's been a long time since the last video. Basically, just been really busy working on the new prototype. If you want to see more on that, then have a look on the Patreon page for that. But yeah, so today's video anyway, what I'm going to be talking about is performance. So first of all, I think it's useful to define what I'm going to mean by performance when I'm talking about it in the rest of this video. So I have heard people say things like hang gliding's chasing performance too much, and it's killing the sport because manufacturers are trying to chase performance figures rather than building sort of gliders that are nice to fly or something. I think there's maybe something there that's worth teasing out, but when I mean performance, I'm not just talking about high speed glide, which I think when some people say performance, that's kind of what they mean. They're just thinking, oh yeah, going really fast. And trying to keep a good glide angle when it's going fast. So to me, that's one aspect of performance. But when I'm talking about it in this video, actually what I mean is all of the aspects of glider performance. So I do mean I include min sync. That's a performance metric which you want to improve. I include max glide as well, which typically get at a relatively lower speed. And also I do mean the high speed glide as well. So really, you can kind of think about kind of the three different areas, but I'd just lump those all in together, and I'm talking about performance. So when I'm talking about improving glider performance, what I'm interested in is improving all of those, not just focusing on one particular bit, like going really fast, for example. And also, of course, at the same time, you've got to, while you're concentrating on that, you've got to also be thinking about handling as well. So I'll be doing a whole other video on handling future, but for the time being, this video we're going to talk about performance. But whenever I say performance, think min sync, max glide and high speed glide, basically all of the glider performance put together, so climbing and gliding. Now in a lot of areas, like for instance think of cars, when we talk about performance, we're talking about you can do it by increasing the power. So you burn more fuel, you use more energy, and it makes you go faster. That doesn't work with gliders. So with gliders, obviously we have a fixed energy source, which is the amount of energy that there is in the air on any given day. So when we talk about performance, what we're talking about now is efficiency, and it's getting the most out of the smallest amount. So in the context of a glider, what we mean by efficiency is lift to drag ratio. So I don't mean here just the L to D max, the maximum glide rate. I mean lift to drag ratio across the whole speed range. So a good lift to drag ratio at low speed gives you good min sync, a good lift to drag ratio at high speed gives you good high speed glide. Because the thing that often seems to get overlooked when people are discussing glider performance is that basically lift is non-negotiable. Like, these are aircraft. When they're in steady state flight, then the amount of lift must always be equaling the amount of weight. And because of the stability we talked about earlier, if you accelerate to a different speed, whatever speed you're flying at, whatever steady state condition you're in, lift is always going to equal weight. So you always have to be generating lift. So what we're looking for is the way to generate the most lift while generating the least drag. Because if we generate more lift, then what that's going to mean is that the glider is going to fly at a lower angle of attack. So it's always going to be generating the same amount of lift. So it's about improving that ratio of lift to drag. Now, where that kind of thinking can lead to is that we concentrate very heavily on the drag side of the equation, and we don't think enough about the lift side of the equation. So a lot of hang glider development over the years has been to do with streamlining and sort of reducing the kind of obvious sources of drag. So treating it a little bit like if you're trying to make a car go faster, it's kind of obvious what you need to do to reduce the drag. It kind of a more streamlined looking shape and a smaller frontal area. Those make it less drag. They make it go faster, and to an extent, that's also true for gliders, of course, as well. So all the improvements that we've seen over the years, the pod harnesses, the more intricate A-frame fittings that reduce the interference drag there. Even thinner wires and so forth. I'm not knocking any of that. That's all valuable stuff, and it all leads to a reduction in the parasitic drag. But by concentrating on that, I think we've kind of getting towards the limit of really what's practical to do there. Whereas what we're leaving on the table, really, that we haven't really done anything like enough development on over the years, is this whole other half of the equation. So, talking technically, this is the induced drag as opposed to the parasitic drag. So at this point I should just quickly go over what we mean by induced and parasitic drag. So starting off with parasitic drag, that's the one which is relatively easy to visualise. So that's just the resistance you get when you try and push anything through a fluid or through the air. So that's the friction of the air flowing over the surface. It's to do with the shape of it as well. You can divide parasitic drag down separately into individual components, which I'm not going to do for this video. For this video, we can just lump all of those components together and just say it's the resistance to pushing something through the air, pushing the glider through the air. So that's the wing, the control frame, the wires, the pilot, all of that together. You try and push that through the air, there's clearly going to be resistance to it. Now, that increases with the square of speed. So if you double the speed, so say we go up from 10 meters per second up to 20 meters per second, you can see the drag has gone up fourfold. Induced drag is the one that can seem a little counterintuitive because it actually goes down with speed. So it's actually proportional to 1 divided by the speed squared. That might seem slightly odd to start with. I'll go into it in a bit more detail in a moment, but for now, just think of it as how hard the wing is having to work. So if you're flying slowly, the wing is having to work the air hard to stay in the air. So this is all to do with what I was saying earlier, is that the amount of lift you generate is non-negotiable. So if you're flying more slowly, that means you're flying at a higher angle of attack, you're working the air harder, and by working the air harder, you're generating more drag. Now, of course, when you're flying, what's really important is the total amount of drag. So if you add those two types of drag together, you get a total drag. Now, what you notice with that is that there is a minimum drag level, a certain speed you can fly, which gives you the minimum drag. That speed is actually the best glide speed. So if you've got the minimum drag, the lift is constant for whatever speed you're flying. We're assuming the lift is constant. So if the drag is a minimum, that means that's the speed at which you get the maximum lift to drag ratio. So that's the speed that you get the maximum glide angle. So you can see from this graph that the best glide speed is the speed where the two drag curves cross each other. So that means that if you're flying at best glide, then exactly half your drag is due to induced drag and exactly half your drag is parasitic drag. Now, if you fly faster than best glide, then parasitic drag is the more important, it's the bigger term. If you're flying slower than best glide though, then induced drag is the more important one. Now, obviously, they do still matter, so even if you're flying fast, there is still some induced drag, and if you're flying slow, there is still some parasitic drag. But the more important, which one is more important depends on what speed you're flying at. Also, bear in mind that this case is for a glider in steady, straight and level flight. So if you're banking, then you're going to be pulling G-force, which means that the wing is having to generate more lift to do that. So say you're really tightly cranked up in a thermal and you're banked at 60 degrees, that means you're going to need to be generating twice the normal, it's a 2G turn, so you're generating twice the normal amount of lift. But induced drag goes up with the square of lift. So that means that at any speed, if you're doing 2G, you're generating 4 times the amount of induced drag. So it also pushes up the total drag by a lot, pushes up the best glide speed by quite a lot. So the point at which the induced drag and the parasitic drag are equally important increases in speed. So that means that all the time you're thermaling, it's very definitely induced drag that's the more important term. In fact, for a lot of the flight, when you're thermaling, soaring, searching for lift, trying to eke out a sort of lifty line and make the most of it, all that time that you're not flying faster than the best glide speed, then the induced drag is the more important term. Now, of course, I'm not saying parasitic drag doesn't matter. It does matter also, and it really matters when you're starting to glide very fast as well. So kind of competition setting, especially on a good day when you can climb very fast and you have to glide very fast, then on those days parasitic drag will be more important. But on a lot of flights, the induced drag is at least as important, if not more important. And I just don't think that we've been concentrating on that as much as we should have been, and we've been too focused on streamlining and trying to minimise parasitic drag. There's a side effect of focusing on induced drag as well. As we'll see in a moment, if you focus on induced drag, you get a wing that's more efficient. That can also mean that it's more efficient at low speeds as well, so it reduces the stall speed, which then means if you've got a lower stall speed, it's easier to land. Potentially you can trade that for a slightly smaller wing area. If you have a slightly small wing area, you have less parasitic drag too. So now's a good time to talk in a little bit more detail about what causes induced drag. So induced drag is drag that's induced by lift, so it's caused by lift. So if we think of lift in the most basic forms, lift is the air pushing up on the wing. That means that it's also caused by the wing pushing down on the air. So if you push down on the air that's flowing towards you, you're going to change the angle of that air. You're going to push the air down, so you're going to have downwash behind the wing. It's actually that change in angle that results in that causes the induced drag. It's deflecting the air through the angle, working the air, creates that drag. So if we want to create a certain amount of lift, and we do, then we have two choices about how we do that. Either we can take a relatively small amount of air and shift it through a very big angle, so push down really hard on a small amount of air, or we can take a large amount of air and push down on it more gently so the angle changes by less. So the second one will produce less induced drag because the angle that you're shifting the air through is lower, then the induced drag is lower. Now this explains why induced drag goes down as you go faster. Because if you go faster, you've got more air per second hitting your wing, so a bigger amount of air. That means you don't have to change it by so much angle. You don't have to push down on each bit of that air so hard, so the angle is less, so the induced drag is less. There's also another way you can get the wing to move more air, and that's by making the wing bigger. So a bigger wingspan, if the wingspan is bigger, it means it's passing through a bigger volume of air. So again, you get that effect that you can push down on a lot of air gently rather than pushing down on a small amount of air hard. So if you look at the equation for induced drag, you'll see wingspan in there. So induced drag is actually proportional to 1 over the square of wingspan. So if you doubled the wingspan, you'd have 1/4 the induced drag. Now I'm talking here about wingspan rather than aspect ratio. So you might have heard before that a high aspect ratio reduces the induced drag. More precisely, it's a large wingspan which reduces the induced drag. Now obviously if you increase the wingspan and you kept the aspect ratio the same, you'd end up with a much bigger wing area. Now you normally fix the wing area fairly early in the design process, probably driven by stall speed. So you're wanting to keep the wing area constant. So as you increase the wingspan, inevitably, if you're keeping the wing area constant, then the aspect ratio increases. If you didn't do that and you just let the wing area get bigger and bigger and bigger, well, your induced drag wouldn't go up with the wing area. The induced drag depends on the span, but if you've got a really big wing in terms of area, then you've got a lot of surface in contact with the air, so you've got a lot of wetted area, so your parasitic drag would be a lot higher. So if we look back at the induced drag equation again, we can recap over what we've learnt so far. So we can see here that induced drag increases with the square of lift, which is kind of interesting, but in a sense that's not terribly useful from a design point of view, because obviously we need a certain amount of lift. The lift has to equal the weight, so that's non-negotiable. We can also see that it decreases with higher speeds, which again, interesting, not terribly useful from a design point of view. If we start to get into the design parameters though, we can see that a bigger wing span reduces the induced drag, and if we're increasing the span, we'll probably want to reduce the chord to keep the area constant, which then leads to the higher aspect ratio. So this is where a higher aspect ratio glider tends to have more performance than a lower aspect ratio glider, because it means it has more wingspan for the same amount of area. Now that is useful from a design point of view. It's something that one of the basic facts that we know about glider design. But also there's a limit to how much we can push this bigger. In the case of a hang glider, really it's governed by the handling. So as we try to increase the wingspan and increase the aspect ratio too far, then you just lose out on the handling. So unless we can do something to improve the handling, we won't be able to increase the wingspan any further than we have at the moment. I will do another video on handling, because I do have some ideas there for how we can increase handling. There are some concepts there, but yeah, let's put that one to one side at the moment, and let's have a look at if there's anything else in this equation we can do. So you can see there's a couple of constants there, can't do anything about those. There's also air density, can't do anything about that, but there's one more parameter here, and it's this one called E. Now E is the span-wise efficiency factor, so this is related to how the lift is being generated across the span, or how the lift is distributed across the wingspan. Because if you imagine that if part of that wing is working really hard and another part is not working so hard, it's not pulling its weight, well, the bit that's having to work really hard is, because the drag goes up with the square of the lift, that's doing so much more extra work, and it's not being compensated for by the other bit of the wing that's not working so hard. Yeah, that bit isn't generating quite so much drag by itself, but it means that the whole wing as a whole is generating more drag than it needs to be, if some bits are doing more than they should be and other bits are doing less than they should be. This doesn't mean that each bit of the wing should be generating the same amount of lift. Now, some bits of the wing tips can't generate as much lift as the wing root, or not efficiently. But what it does mean is that there is a perfect lift distribution. So this is a lift distribution that you can't improve on. It's where every bit of the wing is working as hard as that bit of the wing can possibly work. If it was working harder, it would reduce the overall efficiency. For a planar wing, so that's one without any dihedral, without any winglets or anything like that, just a flat wing, then that perfect lift distribution is an elliptical lift distribution. So what that means is that if we drew a graph of the amount of lift that each section on the wing was generating, then the shape of that graph would be elliptical.
Now, in that little example that I just flashed up on the screen there, that's an elliptical planform wing as well. So that the reason that generates an elliptical lift distribution is because the distribution of the wing chord along the span is an elliptical distribution. Now, if you have an elliptical distribution of the chord, of the width of the wing, and you don't have any twist and you don't have any change in wing section, then you're going to get an elliptical lift distribution as well. But that's not the only way you can get an elliptical lift distribution. In principle, for any plan form of wing, so for any shape wing, you could still get an elliptical lift distribution for it by adjusting the angle of each section of the wing. So we talk about the twist or the washout along the wing. So how does that wing twist along its length, and also by changing the section as you go along it. If you do that, then you can effectively kind of correct for the non-ellipticalness of the shape of the wing, so that you still get a perfect lift distribution. For an elliptical lift distribution, no matter how that's created, whether it's done through planform or through twist or through wing section or some combination of those, but if you have an elliptical distribution of the load on the wing, then the value of E is 1. And for any other lift distribution on a flat planar wing, then E would have a lower value, so 1 is the maximum E can be. Now, if you start getting into non-planar wings, so we have like a variation in dihedral along the wing, or you have winglets on them, it can be different, and the perfect lift distribution in those cases isn't elliptical, but there is still an ideal lift distribution. There is a perfect lift distribution that if you've got the lift spread over the wing in this way, that's the best it can be. There is no way to improve on that. And the thing is, that is potentially something you can calculate as well. There is still some advantage to having an elliptical shaped wing though, because that means that it gives you the elliptical distribution of lift across a very wide range of angles of attack. Whereas if you're achieving the elliptical lift distribution but you're doing it by tweaking the twist distribution, then you can only get that to give you a truly perfect lift distribution at one single angle of attack, and so at one single speed. And at any other angle of attack or any other speed, you're going to be off that perfect distribution to some extent. So in practice, that means that on a lot of aircraft, the wing will be tapered to some extent, maybe sort of a double taper type shape, so that it makes it a little bit closer to the elliptical shape, meaning it's easier to get the elliptical lift distribution by the twist. There's a couple of disadvantages though as well to doing it by having an elliptical shaped wing. The first is that when you get to the stall speed, then it means that because the whole wing is at the same angle, then it all reaches the stall angle at the same point. And in fact, what will probably happen is that the tips will actually in practice stall first in that situation, which is bad. Usually you want the root to stall before the tips. The other thing from our point of view is that if you have that elliptical shaped wing and you have no twist at all, then you can't achieve pitch stability for a flying wing. So if you're trying to have a flying wing which also has an elliptical lift distribution, you actually can do that, but it has to be achieved partly through twist. So then that does mean that you're only able to get that perfect lift distribution for a single design point. So it's hard to talk about elliptical wings without quickly mentioning the Spitfire. So yeah, probably my favourite aircraft of all time, beautiful aircraft, the Spitfire. Had very famously the elliptical planform wing, and one of the things that the Spitfire was really good for was that in a dogfight it was able to turn tight and maintain a tight turn. So for shaking someone off your off another plane off your tail, or for turning inside another aircraft, then it was able to maintain that high G turn. And so by having an elliptical shaped wing, it's not only a efficient wing in reducing induced drag when it's at the normal cruise condition, but it's still giving you that high efficiency even at high G loading, at high angles of attack. So it was able to maintain energy through those tight turns partly for that reason. Although one of the issues for the Spitfire was also that it wasn't the easiest aircraft to land, and tip stalling could be an issue with it. So again, that has its pros and cons. If you think of the Spitfire's main adversary in the Battle of Britain anyway, the Messerschmitt 109, that had a straight tapered wing. Now, I don't know, but I suspect that would have had a appropriate twist distribution to give it a pretty much elliptical lift distribution at a certain speed, because this stuff has been known about for quite some time now, and obviously Messerschmitt was a designer who knew what he was doing, so probably it would have had a reasonably good lift distribution at a certain design point, but away from that design point, so like loaded up in a high G turn for example, then it would be less efficient. And actually it wouldn't just be the Messerschmitt, but for most aircraft, from airliners, sailplanes, most light aircraft, they will be like this is well known stuff, so they will be designed to have a perfect lift distribution at least a certain point in the flight envelope. So hang gliders are actually unusual in that they don't manage to get a perfect lift distribution at any point in the flight envelope. So let's have a look at a hang glider wing for lift distribution then. So the first thing we can see is, just when we look at the plan form, it's not an elliptical shaped wing. It doesn't have the elliptical plan form. It's much more tapered. So the tips are effectively not pulling their weight, and the root is going to be working harder than it should be. And then to that plan form, we're then adding an awful lot of twist to it due to the nature of the wing being made of a fabric, so it naturally twists. So we've started off with a not optimal plan form, and then we've added a load of twist onto that, which makes it even less optimal. Anecdotally also, I heard from a very experienced competition pilot that the glider he was flying back in the 90s, so this is going back some time admittedly, but that if you flew that really, really fast, so effectively diving into goal, it was actually possible that the side wires could go slack. Now that's obviously a wing which is really fighting against itself, because if the side wires to go slack, it means that the outboard section of the wing has to be generating downforce, and then so that means that the mid section of the wing is not only having to generate enough lift to keep you in the air, it's also having to generate enough lift to overcome the downforce that the outboard section's being generated. Now, as I say, that was over 20 years ago, so that's not a modern glider, and we've obviously got an awful lot better since then, but we're still a massive long way off having an optimal lift distribution. So bearing in mind that the elliptical planform wing gave an elliptical lift distribution across all the angles of attack, let's have a look at how a hang glider wing does now. So this is geometry based on the avian puma. It was created for using 3D scan data and then manipulated to try and get it to the correct shape for how the glider will be in the air, although for this it's being treated as a solid unit, so we're not taking account for how it will change in shape as the angle of attack changes. So this is a fixed shape across all the angles of attack, which maybe isn't perfect, but it's not bad. So first of all, let's look at it with the VG loose, and instantly you look at that, you can see that's not elliptical. So it's kind of more of a triangular lift distribution, really, with as you'd expect, the centre doing far more than it should be, and the tips doing less work than they should be. In fact, you can see even at the very lowest angles of attack, so the highest speeds, the tips would be generating downforce in this case. So maybe not enough to make the sidewires go slack, but it's a wing which isn't working optimally. With the VG tight, you can see it is better, which is, of course, exactly what you'd expect, because we know pulling the VG tight gives you more performance, and yeah, clearly it's a lot more optimal in terms of the lift distribution. But actually, when you do look at it in detail, it's still a long way off a perfect lift distribution, even with the VG tight. And of course, with the VG full tight, you've got that compromise in that you stiffen up the handling an awful lot. Now, as I say, this data is generated for the Puma geometry, but it's typical of really any hang glider, especially any sort of high performance hang glider, would have a very similar lift distribution to that. I.e., no hang glider is getting really anywhere close to an elliptical lift distribution, even with the VG pulled really tight. So the question is, why has no one done this yet? And well, I think the first bit of that answer is the analysis. It's difficult. So, although I said earlier that this is sort of established theory, this is theory which has been established since sort of the first half of the 20th century, and it's not that the basic theory isn't understood, and applying that theory to a fixed rigid wing that's not swept and that doesn't also have to provide pitch stability, that's something which it can be done with hand calculations and slide rules and so forth. But to apply that to a swept wing makes it harder. If it's also a wing which changes its shape depending on the air pressure that's applied to it, and it also has to provide pitch stability as well. Now, it's possible to have a perfect lift distribution and also to have a pitch stable wing, but it's really not easy to design that, especially designing it into a swept wing that also bends as the lift is applied to it. It needs some computational firepower to do that, and frankly, it also needs a lot of knowledge to do that as well. And it's not me that did this. That did this bit of the work. So this is someone else, and I'm hopefully introduce him in another video. But it is possible fundamentally to come up with a design for what gives you a perfect lift distribution and also pitch stability at the same time on a flexible wing. The other thing is as well that even the analysis is hard, but also then the building of it is hard as well. So it won't work for just applying it to a conventional hang glider structure. So there's various reasons for that. Maybe we'll go into them in more detail. But to make this design work, to get that optimal lift distribution on a pitch stable design, and also to still be able to have good handling, preferably better handling as well than we have at the moment, that really does mean that you're having to change quite a lot, and having to change quite a lot of things all at the same time as well. It's the kind of thing where if you just do one of the changes, you'll end up with something which is almost certainly worse and possibly completely unflyable. It needs a number of changes to be applied all at the same time, and that's what we're trying to do at the moment. There are some real big possible benefits we could get though if we can really optimise the span-wise lift distribution and so minimise the induced drag. You can get a bit of a clue for how big those benefits could be when you look at what paragliders manage to do. So fundamentally, paragliders have to make some pretty serious compromises in their design to be able to work. So you have to have a very big wing area by the compared to a hang glider, so a lot of wetted surface area. Then you've got the inevitable, all the drag of the lines. You've got the vents in the leading edge as well, so you've got a lot of sources of parasitic drag which you just can't get rid of on a paraglider. So they really shouldn't be getting anywhere close to a hang glider. And yet they really are. Like especially the highest of the high performance ones are now sort of snapping on the heels of hang gliders for max glide at least, and better for min sink rate. And it's only really on the very high speed glides when the hang gliders start to beat them. So if we take as an example the highest of the high performing paragliders, so a triple C one, so these are the ones which are they're really stretching the limits of what can be done with a paraglider. They're very difficult to fly, so you need to be flying well over 100 hours a year just to have the skill level to keep the thing inflated above you. So let's take an Ozone Enzo as an example. Compare it to the Puma. So in the Puma, in the middle range for the Puma is roughly equivalent to the M size in the Ozone Enzo. So let's compare that. So for a start, we can see that they've really stretched the span out as much as they can. So if we're thinking about induced drag, then we're thinking about how much air are you able to push down on. So it probably makes most sense to be looking at the projected span in this case. Now, next video I can talk a little bit about non-planar wings, and that they can get some effect from the sort of flat span as well. But let's just think about projected span for the time being. So 10.5 on the M size Enzo. On the Puma, it's just under 10 meters without the wingtips, and when you put the wingtips on, it makes it about 10.3. So basically, the wingspan's almost the same between a Puma and a medium-sized Enzo. But then when you look at the wing area, well, now because we're thinking more about parasitic drag, we're thinking about the wetted area of the wing that's in contact with the air. So the flat area is more relevant in that context on the Enzo. So 23.7 square meters of wing area. So massive amount of wing area compared to the Puma, which is 13.7. So that's why the parasitic drag is so much higher, even before you start counting for the lines and for the risers and that sort of thing on the paraglider. So the question is, how do paragliders manage to perform as well as they do? And you can kind of get a good clue when you look at the plan form of them. So looking at it, you can see it's pretty well in elliptical plan form. So don't worry about the trailing edge being straight. The important thing is the distribution of the width of the wing along its span, and just visually that looks pretty close to elliptical. The other thing is when you look at the paraglider in the air, you can see it's got very little twist on the wing at all. So again, there's if it's got an elliptical plan form and it's not got any twist, then it's going to have pretty close to elliptical lift distribution. The other thing we know about paragliders is that the manufacturers are pretty much all using a lot of computer simulation and design and analysis when they're doing the design. So again, I think it's pretty reasonable to assume that they're getting a very close to optimal lift distribution out of their wings. So it's that combination of pushing up the wingspan to the absolute maximum they can get it to, and then also having a very optimal lift distribution. That basically explains how the paragliders manage to do what they do. But then if we think in terms of what we could learn from that for hang gliders, well, for a start, we've naturally got much lower parasitic drag. We've also got a structure, so we don't have this risk that the thing's going to collapse when you start trying to push the span up high. So if we're able to crack the handling problem, then we should be able to at least get a little bit more span out of it. But even without increasing the wingspan, if we at least can get the optimal lift distribution out, then we can drastically reduce our induced drag. So then we'd have something with a lower induced drag, much lower parasitic drag than the paragliders, something that doesn't collapse as well. So then you've got something which is better at min sync, so better at staying up in light conditions. You've got something which is better at best glide, so it can glide further. You've got something which is better at high speed glide and able to go faster, and also it waits until after you've landed before it folds up. So that's the direction that I think hang glider development should be going.